All right, Glenn Kirsch. No, I'm not Glenn. I'm Jim. That's right. I'm a math teacher. Yeah. All right. So this is an intellectual exercise with quadratics. I'm getting rather opinionated in my old age. I figure I want to say what I want to say, so I'm going to say it. I think that you have to be able to draw the geometry associated with the early algorithms that we study in order for the possibility of students understanding what they're looking at a much deeper level. So today in an Algebra 2 class, I did the following exercise. I had all the kids at the board simultaneously doing what I'm going to do in a moment, but I can't do it simultaneously. Add area to a bunch of different squares. All right, now, why am I doing this? Let me use baseball as an example. If I was going to teach a youngster how to play baseball, throwing and catching and swinging the bat, ages 5, 6, 7. All right, an awful lot of throwing the ball, catching the ball, and swinging at the ball. But at some point, students or athletes, young athletes, need to be pushed intellectually. You don't hide things in sports. You know, if I was trying to teach how to hit a soccer ball, well, the minute they touch it, I'd be talking about proper shooting technique and not hiding anything. Whereas in math, you know, we kind of go up the ladder slowly from one topic to the next to the next. Now, for God's sakes, if pattern recognition is one of the key goals of a good math class, I think it is. I think pattern recognition is essential. Then how do you show patterns unless you show a lot of different algorithms and say, well, what do they have in common? What's different? All right. So we can't hide things from kids. So at some point, I want to really try to show them what's going on. And in order to do that, I've really got to do some honest to goodness pre-calculus conversations. I mean, we label things pre-calculus, you know, and we do the sine of 7 pi over 6 and everything else. But calculus is about rates of change and accumulation. So how do we get to talk about rates of change and accumulation before we take derivatives and integrate? And that's what this is about. That's the ultimate goal here, is to plant a seed about layering, and you can't do it without pictures. So that's about what I'm going to do. So I guess I'll get at it. Let's hope I've got everything I need ready, because I'm doing all these videos on the fly. I'm not really taking a whole lot of time to say exactly what I want to say, when I want to say it, but trying to plant some seeds. All right, so I drew these squares much bigger all the way around the room. And I had students go up, and I'll do one here. So we were understanding that we have area of a square, and then I'm going to say the words 1 second. And in the amount of time that I say that, they are gonna, with a different color marker, let's see if I still can find that. I do, I have the different color marker. They are going to layer a little more area on the square. So when I say 1 second, they start here and then they're done with that, and their hand should be moving at a constant rate. So 1 second, boom, I added a little bit more area. Now, I probably started with rate times time equals distance, saying it's one of our famous formulas. You know, I would write out rate dot time equals distance. Okay. So therefore, multiplication by time on the left is division on the right. Okay, and rate is, we can think of distance as amount traveled. So let's just talk about amounts, you know, accumulation of amounts. There's the word already used. Okay, not saying anything else otherwise, just accumulation of amount. In this case, accumulation of how much ink you're putting on the board, and how long it takes you. And the length of time is going to be standardized. We're going to think of it as, let's say seconds. 3 seconds ago, we had 9 units of ink, right? 2 seconds ago, 4. 1 second ago, 1. No ink. 1, 2, 4. So we get those nice amounts here, 9, 4, 1, 0, 1, 4, 9. All right. And then we talk about, okay, well, how's it changing in an instant? I mean, when you drive a car, you know, you do a basic, how much has the car traveled in a certain amount of time? It gives us a sense of velocity. You know, so like if we were here and it's 100 miles to Boston and it took 2 hours to get there. Well, I think your brain has already figured out you're traveling roughly 50 miles an hour. I don't know anybody who goes from here to Boston always at 50. I mean, you got to pull out of a parking lot. You got some traffic. I mean, I don't think you just 50. No, you're traveling at different speeds at different instants. And when you look at the odometer, speedometer on a car, it tells you your speed. You know, and speed doesn't matter if you're heading north or south. You need to know your speed. Velocity will tell you if you're heading north or south, but that's another topic. Well, I mentioned it. When velocity is positive, think about heading north. When velocity is negative, think about heading south. But speed is the absolute value of velocity. Now that's a calculus statement, right? That's where you start working with it. Didn't hurt to say it now. This is an Algebra 2 class. It only takes 10 seconds and it's in the brain somewhere. I think we should be doing that. All right, now where's this going? All right, so all the kids, all the students are at the board, and one student's doing this one student's doing that one, and I'll just do what they do all at once. All right, so I say 1 second, right? 1 second, 1 second, 1 second, 1 second, 1 second, 1 second, 1 second. Okay, and what I'm after is, how's your hand moving? Right? Notice when I was at 0, it wasn't moving at all. It wasn't moving at all. Okay. But up here, 1 second, boy, I really should have drawn that on the inside because I'm taking away area. I think I mentioned that to the folks before they did it. So I really should have said, how much ink did I take away? Right? Because what's going on here? 9, 4, 1, 0, trying to talk about decreasing, increasing. And at that point, you know, you draw the parabola and you go, okay, 9 units of area, 4 units of area, 1, no units of area, 1, 4, 9 units of area. Then you can come over here and you go, well, what happened from 9 to 4? Oh, we went down 5 units of area. And maybe you say, well, you didn't always go down 5 to 1 because of the curvature. That's just giving you a reflection of average rate. That's your average rate. Well, how fast were you going down here? Well, we still want to use slope, right? And how do you compute slope? Well, that's when I started doing some numerical work, right? So we got some geometric work there, numerical. And I decided, you know, to have one student come up here and do a 9 by 9 and another student do a 1 by 1. And obviously the 1 by 1, 1 second, the 9 by 9, 1 second. You know, they get a real feel for, at least visceral feel for how things are changing with respect to putting ink on the whiteboard. How much, how fast, right? In the same amount of time. All right, so now I go to numerical. So let's do a 3 by 3. All right, so we've got 3 units of area, 3 units side length, and 9 units of area. And then I said 3 point, and I asked, how many decimal places do you want? You know, and maybe I talked about, how do we talk about an instant? Well, the smallest unit of time changed, that's possible. All right, so what do we want? Let's go with 4 decimals. So I randomly picked 2, 3, 4. I don't care. It could be 10, 20, 30. I don't care how many decimals. You're going to be able to understand what's over here in a little while when I start playing with that picture. Okay, so I'll square this for you. So this is 9.1236, 1, 2, 3, 4. That's what you get. But I'm going to rewrite that in class as plus 0.00004567 And if I add those two things, that's when I get 9.0060001. Okay, and I do this for 2, and I do it for, you know, different numbers and do it quickly. And it was nice. One of the students said, how'd you know that? I said, oh, well, let's go find out how I know that. And then we come over here. And instead of 81, let's say we got a nice big picture. Oh, got to be able to show you what's going on. All right, now you might have to watch this video a few times because I'm going to make some points here that you want to think about if you're teaching this stuff. You're going to want to know this. All right, so 3 by 3. Okay, and in the situation, numerical situation over here, how much did I increase the side length of the square? And hopefully people will get to 0.0001. but I gotta show it. So this is 0.0001. That, and how much did it change over here? Oh, that's another point. I'm gonna put it on the outside though. I am gonna put it on the outside here. This length, it's a square, so that length's the same as that, but I'll write 0.00. I won't even do it there. I'll do it down here. 0.001. So we'll say this went out in this direction and became, you know, I mean, realistically, we have just a thin dental floss with 0.001. So what was this length from here to here? Well, that length is 3. So what do you get when you do 3 times 0.001? You get 0.0003. And what do you get when you do 0.001 here? You get 0.0003. So how many of these do we have? Oh, we got 2 of them. You know, I got a feeling that's where that comes from. Now, where did this come from? Well, really, we got a new little sliver over here, right? And that's 0.0001 times 0.0001. Well, that's that amount. And my understanding is NASA is able to send stuff up into space, and they only carry their calculations out to 8 decimal places. So we're already talking about limits here. Right? I could have pushed this out to 10, 20, 30, 40 decimal places, regardless. Right? So we've already started to plant the seed about a limit. All right, so what's the rate of change? Well, how do we measure rate? Change in y over change in x. So what's the change in y? Hopefully kids will say 0.006. What's the change in x? 0.001. Well, geez, that means at 3, which is up here, I have 9 units of area. And if I draw a little strip, I got kind of a slope there of 6 to 1. Right, and then I'd probably do 2, you know, and maybe I do just 3 decimal places this time. So 2 squared is 4. I'm sorry, I'm on the fly here. And so 2.01, let's do 3 decimal places. So 2.001, and if you square that, you get 4.004001. That's what you get. All right, and then you start to say, well, let's talk about our side lengths, 3 and 2. All right, so I'm trying to get this done quickly. So there's your, you know, limiting experiences out here. 0.004 divided by 0.001, and you've got yourself a rate of 4. At 3, it was 6. You know, I might do 4 next. At 4, it's 8. We go through the same process. And we say, wow, x squared. We got ourselves 2, 3, 4. We got 4, 9, 16. But you know what? The rate at which we're changing, at 2, we're going up to 4 to 1. Oh, here's 2. Geez, that slope isn't as steep as this one, is it? Right? And so you start playing with tangents as reflection of how things are changing in an instant. All right, so you're putting thoughts in kids' head. Because when they get to calculus, it should be there already. All right, the one that I like the most to actually talk about, well, I'm not done with this yet. So that's rates, right? So let me show you where we went next. So the students at this point can put quadratics in graphing form pretty darn easy. All right. Before I even get there, and again, I had planned what I was going to say when I was going to say it, but it's important to know, well, where are you changing least quickly? Or where is it not changing at all? I mean, right now, things look like the rates are going up. Over here, they look like they're coming down. Well, where's it not changing? Hopefully you start talking about a slope of 0 right there. Now, remember when we were doing the 1 second, right? At 0, there was no change in your hand. It didn't move. Why? Because there's no area here. Right? So if I'm going to change it by a little bit, it's going to be a very small positive slope. And at 0, it's actually 0. On this side, it's still going down. On this side, it's going up. So at that instant, there's no change. And that's reflected by a horizontal tangent. I guess if we know when the rate's 0, we're at the vertex. So then I might have done 2x squared, I don't know, minus 20x plus 7. I'll go, okay, so what's the rate of change? Well, we know the rate of change of x squared is double the x value. Then what do? I mean, maybe I should have done a -1 here, -3, just to show that it's going down at 6 to 1. Right, but you know, students, I mean, I may have already lost them. Then I got to perk them back up a little bit, maybe, you know, just get them so I know they're listening again. But planting seeds, not necessarily getting them to, you know, get a great grasp of what I'm doing, might be new for you. And so the pace at which I'm saying this, you know, it's just planting seeds. All right, so x squared is 2x, and I'd say, okay, if you're, you know, your parents said, hey, I want you to look at your brother and I'll pay you $5 an hour, but you know what, I'll double that. They immediately know they're making $10 an hour. So what's the rate function? The rate function, you know, heading towards the calculus, obviously, having a discussion about, yeah, it's a constant rate. When you graph minus 20x, don't you go down 20 over 1, down 20? Aren't you doing the same thing every time? So you got to have those conversations. All right. So putting this in graphing form, our method in class has been minus b over 2a, the average of the roots. And so we use subtraction to get rid of that. So in this case, it's going to be minus 5 squared. That's 50. I don't want 50. So minus 50 plus 7. So that is the graphing form for the one I picked. And they're pretty good at doing, you know, x minus 5. So they're pretty good at doing 5, negative 43, and finding the y intercept. So at this stage of the game, we're really good there. And the question is, if this is the rate and the vertex is in 5, what did we say the rate was set to here? Oh, 0. Well, this is the rate. Let's set it to 0. Oh, x equals 5. My goodness gracious. A different way to find the x value of the vertex of a quadratic. That might be enough right there. And then, you know, I might talk about what's the rate of change at this location. And let's see, I shouldn't have erased that. 2x squared minus 20x plus 7. Because when I ask students to graph, well, let me do a new one. Get you out of that mode. Let's do a new one. And I'll pose the question. Let's do 5x squared minus 3x plus 9. Okay, so how would I graph that? If I was just trying to get a sketch of that, well, I know it's cup shape up, right? And I know that my y-intercept is on the left side, on the decreasing side. How do I know that? That's what I'm going to go show you right now. And I know the x value is minus b over 3a, so 3/10. And then I'd have to put in 3/10, do the math, do the fractions, get that value. And then you got your roots in front of you in 5 seconds or less. So many things you can do. Okay, but notice I started graphing this. You do it, I wouldn't have done it that way. I don't know what I'm talking about. Y-axis. That's all I do is I draw a y-axis and I put the number 9 on there. Okay, right there. That's local behavior. We should be graphing from local behavior to end behavior. Already gives kids a sense of Taylor polynomials before they get there. All right, so that's local. Going down at 3 to 1. And then coming up sharply. Okay, I'd start there. Then all you got to do is find the vertex and you've graphed it. Okay, now how do I know I'm going down at 3 to 1 without teaching calculus? Because I'm teaching calculus without teaching calculus. All right, so what's the rate of change there? Let's do a numeric. Let's throw 0 into the mix. Okay, 0 squared times 5 is 0, minus 3 times 0, and I get 9. Well, let's throw 0.001 in there. 0.001, that's going to be 6 decimal places with a 5. 1, 2, 3, 4, 5, 6 with a 5. This is going to be 3 decimal places with a negative, 0, 0, 3, and 9 hasn't changed. Okay, well, where's the change coming from? This number is roughly 10, 100 times, right? 1,000 times, sorry, 1,000 times. This is 1,000 times bigger than this is, at least decimal, in terms of decimal position, right? So I think we can ignore that. There's no real change there. I mean, we could even push that out again, reinforcing notion of a limit. And there's no change here. Looks like all the change at x equals 0 is taking place with the linear term. Oh, and what is that change? Negative 0.003 divided by 0.001. Oh yeah, it's negative 3. Must be a coincidence. Okay, so just planting some seeds. Again, how are we finding rate of change? A small change in x. So where am I going to go a week from now? A small change in x. Well, when you go to calculus, guess what? That's what that means. All right, so planting some seeds. All right, I took 3 calculus classes. Nobody ever defined dx for me. Numerically, geometrically. Well, I had to start teaching it, diving into it. Go, what am I looking at? What's going on here? Right, because just doing things symbolically, oh, okay, I can kick it back on a test. Well, who couldn't? Not if you put the time and effort in. Right, the real issue is where's this stuff coming from? And for my money, rectangles. And if you look at some of the videos, for instance, the chain rule, I did a chain rule video on explaining the chain rule through the lens of integration. That's how I understand the chain rule. All right, and if you want to, really look at that, it might take you a couple of times to look at it. It took me a lot of years to figure out that video. So you might want to look at it. And I think there's one play. I always make a video with a mistake in it somewhere. That guy integrated from f of x to g of x or something. I threw it into the abstract too quickly in one little part. But the majority of it, I think, is accurate. It certainly shows integration numerically. So you can dig your teeth into some math, some numbers. I do think understanding the numbers is key. But getting to understanding the numbers, I think drawings, pictures, right? And so I just putting it out there. So I will develop this further because I'm preparing kids for calculus. I'd like to see some kids go to calculus and understand what they're looking at. So right now at Algebra 2, we're a week away from graphing sinusoids. A couple of my students are there already processing it. But we've had so many gaps from COVID and otherwise that, I had to start with write the equation of a line. And then I found out, well, got to actually do some fraction work, all kinds of things. But, we're marching there now. And so give some thought to, this where completing the square comes from, right? You start with a rectangle and you turn it into a square. That's drawing, right? And if you want to take that one more step, completing the cube, right? It's in the videos. You might want to look at it. Geometrically, what does completing the cube mean? Right? And that allows you to put cubics in graphing form. There's a video on that. So there's a lot in there that if you want to start looking at holistically what's going on, you're going to have to, I'm going to try to organize those videos at some point. I'm not sure how, but give it some thought. All right, so I'm on a roll here. Must have high blood pressure, but that's okay. All right, so these are private videos at the moment. I haven't unleashed them yet. If you're looking at them, that means I unleashed them. All right. I should have comments available. I'd love to get comments, but I don't know how to even turn them on. I'm not a computer guy. Amazing that I got a YouTube channel. Don't even know how that happened. All right, but if you want to send it's Jim Vollinger, you got my name there, and just Jay Vollinger, and I work at NMH School. Well, I'm retired. That's why I get to say what I want. So Jim Vollinger, Jay Vollinger at nmhschool.org. Feel free to email me. I'm, if you think I'm full of baloney, let me know. I'm happy to find out. That's true humility, knowing who you are. All right, we'll see you. Have a good day.